I guess we'll.
Take over.
So as you can tell from the discussion, we're actually quite interested in some details of the paper ourselves. But let's start talking about this, and maybe we can get to some of these points. So before we jump into the details of this particular paper, I wanted to mention some administrative details, which is that we've actually posted Lab 4 on the website if you want to take a look at what's going on there. And the reason I mention this is that there's several options that you guys have for Lab 4. So there's a default that is very much in following the first 3 labs, where you are going to prove a replicated disk correct with crashes. And this uses the same lab infrastructure that you guys have been using so far. But we wanted to also give you guys an option to do something else. And the suggestions that we have on the website right now are largely around learning another framework or another system. So if you want to learn more about Daphne, which is some of the tools underlying this paper, for example, we have a concrete set of things you could go and do to do that instead of doing the default Lab 4. Same for Iris or another tool called VST if you want to learn that. And if you want to do a very free-form final project, if you have something else you're just burning to do, that's also fine with us. But if you're doing one of these non-default things, tell us soon so that we know what's going on and that we can guide you to an appropriately scoped size non-default Lab 4 that's not too big and not too small, and it's going to work out well for you guys. Our intention is not to sort of get you guys doing something extremely difficult here. So the hope is that you'll learn something, and we're expecting that we'll sort of give you good credit if you learn something about another system. But anyway, get in touch if you want to do something other than the default replicated disk for Lab 4, and you can take a look at some of our suggestions. So that's the administrative things. Any questions about that? All right, well, you can send us email or ask on Piazza if you have something concrete you want to ask about. So the focus of this lecture is this paper on Armada, which is a recent system. The paper came out less than a year ago. Actually, this appeared at PLDI a couple of months ago, actually. And the reason we're reading it is that it's an example of a system that really takes to heart this goal of having a machine-checked proof of concurrent software. And so far, we've been sort of dancing around this issue, looking at why concurrency is difficult and what shared memory means. And Butler talked on Tuesday about sort of the foundational way of thinking about concurrency, either as a state machine or as a language level thing. And now we're going to look at actually what it takes to prove some piece of concurrent code correct. And there's a couple of cool things going on in this paper. We'll look at some aspects in the lecture. So one really cool thing is that these guys are really going after the hard kinds of concurrency. And what I mean by this is that it's not just grab a lock, do a bunch of stuff, and release the lock, and that's the kind of concurrency they're doing. But really, they're trying to tackle much more general cases. They sort of sell it as, well, we want to give the programmers the flexibility to do anything. But indeed, they're able to realize fairly tricky pieces of concurrent code. So they have some lock-free data structures that they prove correct. So there's no lock held. There's just threads accessing memory locations in a carefully orchestrated way. And it's tricky, but they show that they got it right. They also have a realistic memory model. So they literally have a model of x86 TSO, very much like we talked about a couple of weeks ago in lecture. So they have threads running on top of this weakly consistent memory at the TSO level, instead of pretending like it's sequentially consistent. So that's really cool. They're really biting off a hard problem here. Another thing to sort of keep an eye on in this paper is that this paper for us is going to exemplify the kind of state machine reasoning that Butler talked about. And what we're going to actually look at is 2 papers. This lecture is going to be about how to do stuff at the state machine level, thinking about the system as transitioning from state to state to state to state, and how that interacts with concurrency. And then next lecture, next Tuesday, we're going to actually look at a paper that's or a system that's very different, that takes takes a language view of the problem, and as a result arrives at a fairly different design for dealing with concurrency. So it'll be interesting to sort of contrast what you see here in this lecture and the next lecture on the system called Iris, which is all about language level concurrency support. So that's the other sort of reason we're setting up this paper to discuss. Then in terms of the meat of this paper, it's really all about proof strategies. So at some level, what Butler talked about on Tuesday is the basics of here's how you just think of concurrency. There's many possible transitions corresponding to perhaps different threads taking a step at any given moment. And the problem is, how do you reason about this large set of transitions? And this paper actually does a pretty good job of laying out various ways you might go about doing that. And it's sort of easier to see in this paper because they take the state machine approach to thinking about concurrency. So it's easy to see them sort of at some level struggling with this large set of possible traces up front and then shrinking it to a smaller set they have to worry about through various proof strategies that the paper describes. So it's interesting to also look at it from this lens. And all their proof strategies, as we're going to talk about, really build on sort of two basics that are probably not going to be too surprising. So they have invariants, which allow you to reason about what must be true at all points in the execution. And they show these invariants hold for all possible executions of the code or state transitions. And the other sort of basic underlying thing for them for reasoning about concurrent code is state abstraction, or these abstraction relations are. So invariants and this abstraction relation are the foundation of how they reason about correctness of concurrent code. And then on top of this, they have several proof strategies. And the big thing here, the big idea to pay attention to is this notion of a reduction. Or they sort of also use the term movers in some places, and we'll use the term movers in this lecture as well to some extent. And this is the core idea for them for how they're going to be able to have code that's really fine-grained, interleaved at the level of instructions, but then prove that it's actually equivalent to a spec where everything happens at once. And this atomicity of everything happening at once is going to simplify the spec for them. And most of this power is going to come from this reduction idea. So we'll spend most of the effort trying to understand how this reduction works for them. And then they have a bunch of sort of, auxiliary, if you will, helper strategies that basically help line up the problem in a way that reduction can take place. So these helpers are things like this TSO elimination strategy that they have that basically, if you follow some rules, you can pretend like you have regular memory, sequentially consistent memory, rather than TSO memory. And they have this also weakening strategy, and a couple of others. And their role in life, in Armada's life, is to basically sort of massage the problem so that reduction can come in and make things atomic. And then maybe they do more massaging, and then reduction comes in again. So the way to think of it is that the big proof strategy is really reduction. That's what's going to make big atomic units for us. And then these other helper strategies are going to be there to enable reduction to be possible. And then they have this idea of levels, or other systems have other forms of this modularity, layers, and whatnot. The details are not super important at this level of discussion, but it helps them really modularize the proofs and make these strategies fit together in some kind of a coherent style. So we'll look at this in more detail. So that's the sort of main intellectual sort of push of this paper is on these proof strategies. And another actually big push for them is really on automation. So the paper in a number of places talks about trying to reduce the proof effort, make it easier to reason about concurrent code. It's a little bit hard for us in this class, or at least in this lecture sequence, to appreciate some of the cool stuff going on in the automation space for them. I'll try to highlight a couple of things where they have interesting design decisions that are good for automation. We haven't really been looking at how to reduce proof effort in this class as much. So probably this discussion isn't, we're not going to spend as much time trying to understand their cool ideas or contributions in this automation space.
It might just be worth pointing out, though, that when you take the state machine approach to concurrency, it's pretty much essential to have automation because there's so many cases you have to worry about, or somebody has to worry about.
Absolutely, yeah. So that was a good point. I was going to get to it a little later, but I might as well talk about it now. So as Butler mentioned earlier on in his lecture on Tuesday, you can think of concurrency from a state machine level where you just imagine, clock cycles in your hardware maybe, or something at that level, where some really small transitions happen, and they happen atomically, one at a time from multiple threads or multiple execution contexts. And at that level, everything could be boiled down to a state machine view of the world. And the problem with that way of reasoning is that you quickly are overwhelmed by the number of transitions you have to reason about. But the cool thing is that in some ways, the reasoning is broad, but maybe not so deep. I don't mean this in a pejorative way to say that they're doing boring stuff or anything like that at all. What I mean is that the state machine way of reasoning requires you to consider lots and lots of cases, but these cases are, relatively speaking, not that hard to think about. Whereas in the language view, which we're going to talk about next week, there's fewer cases to consider by design. There's things that are sort of mostly sequential, but there's a lot more sort of hard things you have to invent or cook up as a proof developer or a software developer in this language level view. And as a result, it's really hard to automate that because there isn't sort of a mechanical question you could just ask a million times. It's really sort of one question. What's your separation logic invariant or resources that you own? That's trickier to pin down. Maybe some of this discussion will make more sense after Tuesday's lecture. That's sort of the contrast. And indeed, I think the big reason why these guys go for a state machine approach is because it's really, you can think of a state machine approach as really amenable to just brute force search. You can just, worst case, try to think about all these crazy many combinations. That's not going to fly because there's too many, there's exponentially many, but at least there's a starting point, and now you're basically in an optimization question. How do you shrink the exponential space to something manageable, as opposed to some kind of a other problem where like, well, you got to come up with some creative invariant to make this fly at all, and it's not an optimization question. So hopefully this will make some sense after this lecture, and maybe even more sense after Tuesday's lecture next week. All right, any questions so far about sort of Armada, what's going on, etc.? Actually, well, one of the sort of students auditing the class, Upamanyu, is, if you noticed, he was one of the co-authors in this paper. So he's the real expert. So actually, we're like Butler and me are quite interested in asking some things about Armada as well, but feel free to also jump in. It'll be an interesting discussion for us, at least, hopefully for you guys as well. All right, so let me talk about what the sort of overview is to give you some maybe hands-on-ish feel of what is going on in this Armada thing. So one way to think about it is that the starting point is they have a language, the Armada language, and it's kind of like C or Daphne, but Daphne is sort of a weird starting point because probably none of you guys have really used Daphne, and that's not a useful comparison, but it's kind of like a low-level-ish language like C, but they have some extensions to make it more like a spec. What I mean by this is that you've probably seen in the paper, they have some constructs in their C-like language that are kind of like existential or non-deterministic. So they have this if asterisk operator. So, well, go either way. It's like a bizarre statement in C, but for a spec, it sort of makes sense. And they have this also somehow operator that says, well, cook up a value that just happens to be good according to this predicate. Not a sensible thing in C, but works well for them in this spec context.
It's actually not ridiculously different from pluscal.
Yeah, actually, yeah. So
pluscal might actually be a better comparison.
Yeah, good point. Yeah, so like pluscal is actually, I think, a good. Well, pluscal is not C-like in quite the Armada sense, but yeah, so it has some of those aspects indeed.
Yeah, the way I like to think about it is Armada has two different worlds. They have the world of the code, which is very C-like. In fact, they have automated translation of it into a subset of C. And then they have the spec code, which is much more like +cal.
Yep. And they sort of use the same language, I suppose, to make the correspondence easier and to make the development of the tool easier. But the same language in their case gets used basically for two things. So they have a spec written as a little Armada program. And this Armada program, as you saw in the paper, is a description of what you expect the system to do in maybe abstract steps, where you have big atomic chunks and these somehow statements, etc. And then at the bottom, you also have real executable code also in this Armada program. And then what happens is, maybe let's get the executable stuff out of the way first. The code just goes through this code generator that they wrote and produces a .c file. And this thing, you can imagine, you could run in a number of ways. They choose some CompServe variant to compile it, but really it's C code. You can run it and get an executable program. But the interesting thing for us is how are they going to reason about the correctness of this code? So as I mentioned, they have the state machine approach, partly or largely for the automation benefits. So what they do is they actually have this box that they implemented, which is the state machine translator. And what this translator does is it takes in this Armada code and then prints out a state machine description of what this code does. And this looks like, in some ways, a very unwieldy, crazy thing, because all of a sudden, okay, so what is a state machine description? There's a question of like, well, here's the states of the program, and probably this means all the memory content and some number of threads that are running, and for each thread, there's a program counter, that's where we are, and some local variables, so very sort of expanded out state of the world, very explicitly stated. And then they have transitions, or steps. And these are sort of descriptions for every line of code, or for every sort of primitive atomic operation embodied in the Armada code on the left here. They're going to emit a transition saying, well, if I had some thread whose program counter was right at that point before the atomic step, then I'll emit a transition that changes the state to move down to the next program counter and update the state, like the variables or shared memory, accordingly. So it's very explicit sort of expansion of the program into these state machine transitions. The cool thing is that now these things are kind of like small. Each one of them is a little step. There's thousands or maybe millions of them, depending on your program size. They're all sort of small and fairly simple on their own right, each individual thing. All right, and then they're going to do the same thing to the spec. So the same kind of a translator is going to output also a state machine description for what the spec describes. And the goal for them for correctness, as has been throughout our whole class, is to show a subset relation, right? So the set of possible executions of this code is a subset of the possible executions of the spec. So everything that the code does is actually okay by the spec. It's part of what the spec allows. The way they're going to do this is they have another thing that the developer writes, which is this thing called a strategy invocation. So the developer says, I want to use this strategy. We talked about them a little bit on the previous board, reduction or elimination or weakening. And this guy goes into a proof generator. And this thing takes the strategy, and there's probably some hints along with the strategy of how to apply reduction, which program counters matter, where's the movers, etc. And this proof generator actually prints out a whole bunch of proof scripts effectively. So if we were doing this in Coq, the way you would think of this is that the states and transitions are a whole bunch of Coq definitions that get printed out at the bottom here, and then you get a bunch of Coq definitions or some definitions for the state machine at the spec level. And these proof scripts are a whole bunch of these tactics that you would see in Coq that try to prove this subset relation. Except that in their case, they're actually not using Coq because Coq is not that great at helping you automatically solve lots of little goals. It's really tedious to write those proofs. What they use is a system called Daphne, which sort of confusingly is actually its own little verification language, and you can write code and verify it in Daphne. But they use it basically as a, a logical checker or automated proof.
As a theorem prover, basically.
Sorry?
As a theorem prover, the same way you'd use
I
Coq.
guess as a theorem prover, but maybe like a different qualitatively kind of a theorem prover than Coq is. Coq is very much expecting a lot of input from the developer to prove the theorem, whereas Daphne really tries to use lots of techniques using SAT solvers or SNT solvers like Z3 behind the scenes to show the subset relation. And this proof script, has to give Daphne some hints and some structure, but it's much more perhaps automation friendly for this kind of pipeline.
Yeah, maybe this isn't quite right, but I think of Daphne as a front end to Z3.
Yeah, I think this is the way they certainly use it. Although in some other cases, Daphne can be thought of as like a programming language of its own. In their case, it's basically a wrapper around Z3. Yeah. Oh, Humani, you were going to say something? All right, so that's, I think, the sort of overall structure. And then they have this levels or layers, I guess, levels thing, where they actually allow you to write sort of multiple of these spec levels, and they sort of keep going up the stack. So you might have actually multiple of these Armada programs that are specs, and you sort of slowly massage your code to be more and more abstract and perhaps closer and closer to what you ultimately think is going to be spec at the top level of this layer diagram I'm drawing on the slide. That make sense? Questions about this? So I guess I should say on the right side, basically like all these three things get fed into Daphne, and Daphne probably says okay or not that this sort of implementation is a refinement of this spec given a bunch of these proof statements or scripts that Armada generated. All right, questions about this? Okay, so let's try to understand what's going on for Armada in terms of this sort of state machine business and why are state machines particularly useful for them. So how do you use state machines to reason about concurrency? So what's going on in Armada at some level where the programmer is writing source code in their language. So you might have multiple threads, thread 1, thread 2 over here, and these threads might have multiple statements, A, B, C here, X, Y, and Z over there for thread 2. And the way Armada deals with this is, first off, they transform these threads that might have multiple statements into lots of possible transitions that can happen. So basically, if thread 1's program counter is at this position, then a possible transition is to take the A step and get to this other position. And then you can take the B step and get to this other position, and so on. And what Armada is trying to reason about are the possible executions given all these transitions corresponding to the sort of threads that are running. And the way we're going to try to draw them out is that we might start with some state S over here. And then there's multiple transitions we could take from that point if we're sort of just starting out these two threads. We could take the A transition in thread 1, and then we'll be in some state, S1 over here. And then we might take the B transition. So this is corresponding to us running the first thread. And then, we might decide, time to run the other guy. We'll do the X transition from the second thread. Here's a state S3. But this is not the only sort of set of possible transitions. At the beginning, we could have also decided, we'll start out running thread 2, and here's S1 prime. Or maybe at this point, instead of running B, we might have decided to run the X operation right here. Here's an S2 prime. And lots of states, as you can imagine. At every point, at the very least, every thread has a chance potentially to run. Maybe there's other non-determinism involved, and so on. So there's quite a large number of these executions over here. And on the left here, we were writing these threads as sort of a piece of code. On the right, we might have sort of a spec version of the same system, also written as threads, but maybe the transitions are simpler. So maybe there's like a big A transition here and a big X transition over here. So there's maybe fewer possible executions on the right. So you could do A, and then you could do X, or maybe you could do X, and then you could do A. And Armada's goal is to basically prove this subset relation. So all these crazy sort of trio of executions on the left with fine-grained interleaving between all the threads is a subset of the possible executions we see on the right for the spec level. And here it's maybe easier to see what we meant earlier by having this be automation friendly, because what's going on is that at some level, it's a very mechanical thing. You just got to explore this gigantic tree on the left, and for each one of these guys, demonstrate a possible state transition on the right. Actually, there are some better ways to even encode that problem, but sort of a very broad question. Lots of possible executions. You just got to consider all of them. It's a good thing for brute forcing. And as I alluded to earlier, brute forcing doesn't quite work out, but it's kind of a good fallback. If other strategies that Armada has don't work out, you could at least brute force. And in some cases, I think this sort of boils down to brute forcing in some sense. Make sense? Questions about sort of what's going on, or like what these state transitions, where these state transitions are coming from? All right. So let's look at sort of one example from their paper. So they have this example of trying to prove that sort of here's a piece of code on the left. This is probably executable code. Sort of depends on what this condition and do something are in these boxes. But roughly speaking, we can imagine that maybe these things, I'll call them A, B, C, and D for sort of the unlock statement, the condition check, the do something, and the unlock. So here's the 4 statements on the left. And there's many ways in which these statements could interleave with other threads. And the goal is to show that it's a refinement of this high-level spec that says that, well, let's try to figure out what is the spec. So you probably saw this figure from the paper. So one interesting question is like, what is the spec even saying about the behavior of the code? So this explicit yield statement is a thing they borrowed from another system called Civil that some of the authors built earlier. And the idea is that on the left, in real code, you could have interleaving at every possible point. So you might have another thread come in here at this blue point, or here, or here, or here, etc. And that's a lot of interleavings to reason about, corresponding to this giant tree I was showing on the previous slide. So these blue lines are all these sort of yield or preemption points where you got to consider many possibilities. And this explicit yield statement on the right, what's basically saying is that there are no blue preemption points like I was drawing on the left. The only blue preemption point is right here when they explicitly say yield. So what the spec is saying, it's the same code, but like syntactically, it looks like the same code. But the really cool thing is that the spec implies that you don't have to reason about preemption happening anywhere else other than this blue yield statement. And this is, they're sort of building out these bigger atomic units of execution that's going to help them simplify the spec and reason about it. And what this implies in terms of the traces, I think this is maybe somewhat of a repeat of what I was showing in the previous slide, but on the left-hand side, what you have to worry about is all the real executions of different threads. So you might have thread 1 doing the A transition, and then maybe another thread comes in and does something unrelated, some kind of an X. And then we are back to running thread 1 and does this B statement, which is the condition check. And then maybe it gets lucky and runs the do something back to back. But then another thread comes in and then does a Y. And finally, we get a chance to do our D unlock statement over here. So here's an execution where thread 1 was running, but then thread 2 jumped in 2 places and did something else. Well, there's many of these green traces like this that I've shown on the left. And the cool thing on the right is that it's a much smaller set, right? So basically, because there's an explicit yield point, the only possibility is that we start from some state S, a related state to the state S on the left, and either thread 1 does everything, A, B, C, D, and there's no interrupting it. It's one arc. It's a big jump. It's the same A, the same B, the same C, the same D, but they all happen at once, one state transition, and then maybe thread 2 gets a chance to do its stuff, X and Y, whatever else. Or thread 2 goes first, but then we do our big jump right away, A, B, C, D. So this is the cool thing about their explicit yield statements, that the spec is capturing the notion that you expect this region of code to all happen at once in an atomic region. And then sort of similarly for this bottom region, although maybe it's less interesting. And then sort of, I guess, a third region that's a little bit harder to show is sort of you do this lock and then you go around the loop and you do it again. But so all the possible executions that don't have a yield statement have to be atomic in this explicit yield region. Make sense? So that's what their spec is saying with respect to building up bigger atomic units. And this is where their reduction plan is going to come in. They're going to try to reason about the code sequences like we see on the left here at the low level and argue that actually it's all the same as if we had these big atomic jumps. This is really the core of their sort of the big strategy they have for dealing with concurrent threads and sort of interleaving. Any questions about this so far? All right. So let's talk about how this reduction plan is going to work for them. So what reduction does, maybe let me grab a blue color again, slightly more visible. So this reduction or movers proof strategy is going to help them make that case that I was trying to sort of show on the previous slide about making all those transitions atomic. And it revolves around the notion of certain transitions being right movers or left movers. And we'll see what this means in a second. So what they're going to do is, just to give you some intuition, so a right mover might be something like acquiring a lock, and we'll see why it's a right mover in a second. And a left mover is perhaps releasing the lock. And in order to demonstrate what it means to be a right mover or left mover, let me draw one of those really interleaved traces of execution that I showed on the previous slide. So we're going to start out with some state S. Then we have thread 1 doing the lock. Then some other thread jumps in, does an X. Then we're back to thread 1. It does the step B. Then thread 1 does the step C. And then, again, thread 2 jumps in, does something else. And finally, we're back to thread 1. It does the unlock. So this is the same history of trace execution I was showing in the previous slide. I just sort of substituted in the lock and unlock for A and D, which were the names for those things in the previous slide. All right, so this is, okay, the plan for reduction is we're going to consider these traces. This is reality, but we don't want to reason about them directly because there's too many of them. And the insight we're going to cook up or use is that it's possible to move a lock in this trace to the right. That's what it means for it to be a right mover. So maybe more concretely, what do I mean by this? I can take these two operations and I can transform them. The way I'm going to transform them is going to start out from the same state S, and then I'm going to pretend like actually this X from thread 2 happened first. And then I'll pretend like then we actually did the lock. And what it means for these guys what it means for lock to be a right mover is that if we ended up in some state S2 over here, let's say, then it's going to be the same state S2 over here when we reorder them. So it doesn't actually matter whether the lock happened first or this other guy happened first. It's always fine to take the lock operation and move it to the right. And the same thing is going to be true for the unlock, except that it's a left mover. So what it means to be a left mover is that, let me denote these states with something concrete, like let me call this guy S4, and this will be S6. And we're going to do the same trick. We're going to take these two operations and we're going to say, if we're in state S4, and in reality, what happened is that thread 2 went first, what we're going to do is we're going to actually pretend like thread 1 actually went first instead. Thread 1 did the unlock, and then ended up in some state, and then we'll pretend like thread 2 ran. And what it means for the unlock to be a left mover is that if we do the swap, we will end up in the same state S6. So these left and right movers are these kinds of, commutative operations in a certain direction. So here's why this is cool. If we swap the lock this way and the unlock the other way, then, in the middle, this section is actually the same and unchanged. We could just move these operations as is. We still had 1 doing the B, and then we went to some kind of a state S3 in the middle. It's the same state, actually, because we started from S2 over here. So if we do the same operation from the same state, we will be in the same state S3 as we had above. And then we'll do operation C, and finally do the unlock. And look, the cool thing happened here. This region is now all thread 1. It's as if thread 1 is doing all these 4 steps back to back. And we can basically then pretend like, well, actually, that's what happens. Thread 1 does all of them. Lock, then A, lock, then B, then C, then unlock. And now, once we do this transformation, we can reason just about this one nice state. There's many fewer of these guys because we put all the 4 operations of thread 1 together. So the way to think of this reduction strategy is that it takes all these real executions at the top. It shows that every real execution with lots of fine-grained interleaving is actually equivalent, some kind of an equality, to an execution where we move these locks and unlocks and other movers together, squish them into a contiguous region where thread 1 is doing everything all at once. And then we can pretend like it's just this all at once. And once we've reduced the number of traces we can consider, we just need to take these nice sort of traces at the bottom where these guys are all together, and then we can show that they are a subset of the spec. And because the top and the bottom here are equivalent, it implies that this guy is also a subset of the spec. So that's the core of this reduction argument. We're going to use this mover insight to reduce the number of possible state machine transitions we got to consider for showing the subset relation with respect to the spec. That makes sense? Questions about this reduction plan? In some ways, this is sort of the core of their paper. This is sort of the big idea they're using to make their proofs work out, or their sort of prove very nice, clean atomic specs for their systems. All right, so the general case, or sort of the general pattern, if you will, for how to apply this mover insight is that in order to take a chunk of code like this lock, B, C, unlock sequence, if you want to show that this thing behaves as an atomic unit, then basically you have to show that your code looks like a bunch of right movers, so some kind of a right mover, so on, a bunch of them, followed by maybe one non-mover indicated by this N letter, and then a bunch of left movers. So if your code looks like sort of this sequence of right movers followed by some non-mover, so non-mover is something that like doesn't even necessarily need to move anywhere, and a bunch of left movers on the other side, then what you can imagine is that we're going to take this non-mover in the middle, and we're going to squish everyone towards the non-mover. What I mean by squish is we're going to consider every possible trace that this code, the general pattern, can produce, and it's going to be an R followed by some other threads, another R, other threads, another R, other threads. and then we'll have the n in the middle. The n isn't going to go anywhere. We're going to take all the r's and push them towards the right, so they squish up against the n. So then the r's are right away atomic with the n, and then we'll take the L guys and we'll push them left, so they squish up against the n from the other side. So what it looks like is an execution that has all the r's, the n, and all the l's all happening at once, back to back. And because they're back to back, we can pretend like it's a single atomic transition. That's the general mover strategy that the Armada, the paper talks about, and they sort of describe this pattern of R's and L's on the left and right, respectively. That makes sense? It's a pretty powerful idea for how to sort of deal with concurrency. Now let's try to dig a little bit deeper in terms of...
Nikolai, there's a question in the chat. I think Caleb's audio doesn't have audio.
Well, you know, the Linux Zoom client is a little bit horrible. I can't actually see the comments. Maybe Tej can...
Yeah, I can read it out. So, okay, I see that you can move 2:y and 1:unlock. What if you had an interleaving 1b, 2y, 1c, 1unlock?
Yeah, okay, so that's a good question. So I think the question that Caleb's asking is, let's consider another execution, which is maybe like, you know,
1b.
Let's look at this like middle region, basically. So instead of thinking, like I sort of lined up my example just so it worked out very nicely for me. But I think what Caleb is saying is like, well, what happens if actually what was going on is that we had 1b and then some other thread, maybe even 3, came in with a q. Who knows what the hell is going on, but like came in, and then we did 1c. Well, I think you're exactly right. You got to worry about this possible execution too. I think this is another example of probably the trace that Caleb was describing. I think he was trying to move the 2y into here, but same thing. So what the hell is going on here? How do we get rid of this? Well, the trick is actually that I said that the lock was a right mover, but actually there's more stuff that's a right mover. In particular, the B is also going to be a right mover, and the C is also going to be a left mover. Actually, what's usually the case is that actually both B and C are left and right movers. So lock is only a right mover. It can only move to the right. And one way to get the intuition for this is that if you grabbed a lock at time 5, then you can actually pretend like you grabbed the lock at time 7, because no one else could have grabbed the lock between 5 and 7. You were really holding it starting at 5. So you can just pretend like you got lucky and you got it at 7 instead. It's not okay to move the lock to the left, because if you got the lock at time 5, you cannot pretend like you got the lock at time 3. Someone else might have been holding it at time 3. So lock is only a right mover. Same thing with unlock. Unlock only moves to the left for the same intuitive reason. If you released it at time 10, I can kind of pretend like I released it at time 9, because no one else should have been looking at it until after time 10. That's the only time when I released it. But the stuff in the middle, the B and the C, these guys turn out to be actually both movers. What I mean is it's both a right mover and a left mover. It commutes in both directions. And the reason for that, likely in this example, is that no other thread is going to do anything that conflicts with B or C, because B and C are protected by the lock that thread 1 just acquired. So maybe an easy way to think of this is, let's suppose that the lock just protects some literal physical memory locations. So if I grab the lock, then B and C are going to access those memory locations. No one else can be touching those memory locations because they're not holding the lock. This means that if they're touching a different set of memory locations, like this Q operation, it must be touching a disjoint set of memory locations from B and C. And this means that I can move the B across the Q either way. They're just completely talking about different things. They're touching different memory locations. They have nothing to do with each other at this sort of microscopic scale. So indeed, the answer to your question is that actually both the B and the C operations here are probably both left and right movers. And this means that you could actually like squish them past the Q whichever way you want. It's possible to be slightly more general, which is this N thing in the middle. So it might be that like maybe C for some reason is a weird operation that's not a mover at all. So it would have been okay if maybe C was a non-mover, but then B was a right mover. Also would have been okay if B was a non-mover and C was a left mover. All would have worked out. But indeed, something has to move there in order to deal with the possible 3 guy in the middle. Hopefully that answers your question. All right. So let's see. The next thing I want to talk about is how do we convince ourselves that things are movers? So far, I've sort of painted this magical picture where we can reorder operations, but like I'm sure not every reordering is valid, right? Like I can't just reorder stuff willy-nilly. I gotta have a machine check proof here that this reordering is valid in order for this to be a meaningful proof that I got my concurrency story right. And the way that's gonna happen is that we are going to actually use Daphne to prove that the certain operations are movers. So what does it mean to do one of these mover proofs? So just to sort of maybe back up a second, on the previous slide, what we were talking about is the whole reduction strategy. And the way this is going to work in Armada is that the developer is actually going to tell Armada, look, this region of code is a mover pattern or a reduction pattern, and it's going to actually specify ranges of code, which are right movers, and then ranges of code that are left movers. And then it's up to the developer, the developer specifies the sort of mover regions, the right movers and left movers, and then Armada, with Daphne's help, is going to check that every single thing in the right mover region is indeed a right mover, and every single thing in the left mover region is indeed a left mover. And so that's where we're going to talk about what we're going to talk about now, which is this question, like suppose that one of the operations in the right mover region that the developer talks about is some transition T. And we want to figure out, is T a right mover? Well, in order to answer this question, we really have to sort of consider how T can move with respect to every possible other transition. So one way to think of it is, we're going to start out with some state, let's call it S1, and we're going to take the transition of T by, some thread I. We're going to end up in state S2. And now we have to consider every possible other thing that could possibly happen at the same time. So, some other thread J is going to make some other transition X, and we're going to end up in state S3. And this is going to be a highly, quantified theorem. It says, for all possible threads J and for all possible transitions X that J can take, if this happens, then, well, what do we have to show? In order to show that T is a right mover, we have to show there exists another state S2 prime, so that you can start from S1 and then do this J transition, going to the J thread doing the X operation, then jumping into S2 prime, and then finally doing the T transition here. And we have to end up in the same state S3. So sort of the crux of it is we swap the operations and we must demonstrate that the resulting states are equal. And part of showing this is we got to figure out, well, what is the state in the middle that J can go to, and then we can do the T afterwards. So this is the sort of crux of what Armada poses to Daphne. And as you can imagine, this translates into lots and lots of little theorem statements, mostly because of this quantifier. There's like lots of possible J's and lots of transitions that another thread J could take. But this is something that Daphne is potentially going to be good at because it can brute force a lot of these checks mechanically. And just to give you some intuition for how this proof might go about, we're actually going to leverage the invariant in order to argue about this. So one way to think of it is that, suppose that we know that I runs T. Well, let's imagine this T is perhaps that B operation we had before. It's like in the locked region. Well, maybe T is something that only happens if you're holding a lock. So this means that I holds the lock, and this means that J doesn't hold the lock. And consequently, this means that J cannot run any transition Z if Z requires a lock. So you can rule out the possibility that this operation X is something that also needs the lock to run. And now, if it turns out that all the other possible transitions in the system either operate on a different set of memory locations, or they operate on the same set of memory locations, but also require the lock, then you can sort of prove this, because either they need the lock and they can't have the lock, we are holding it, or they're just operating on disjoint memory, and it's commutative because they have nothing to do with each other. So this is a sort of a somewhat vague, but hopefully intuitive sketch for what this reasoning looks like that Daphne and Armada are doing in order to do this analysis that something is in fact a right mover. That makes sense? Questions about this? All right. So there's one sort of technical detail that turns out to be really difficult to automate. And it's actually that this exists S2 prime. This turns out to be very difficult for automated theorem provers to instantiate on their own. So the way that Armada deals with this problem is through something they call non-determinism encapsulation. So on the previous slide, I was just drawing these transitions as many possible arrows that could go from a given state. So there's many transitions you could take. That sort of makes it complicated, like which state do you end up in? This transition is really a relation between two states. It's hard to compute mechanically on this. So instead, what Armada does actually makes it a very deterministic function, but sort of pulls out all the non-determinism into an oracle of some sort. So there's this next state function that Armada has, which takes some state S and a step sigma. And this guy gives us another state S prime. So this way, all the non-deterministic choices that a transition was making is really encapsulated in this sigma object. And as a result, the picture looks kind of similar, but much more amenable to automation. So we start out with state S1. And first, what we're going to do is take the next step from S1 with sigma in thread I. So that's our transition T from the previous slide. And then we end up in some state S2. Then we take the next step transition from this S2 and do the sigma J. This is the arbitrary X transition by some other thread. And we end up in state S3. And the mover check is the following. We're going to take S1 and apply the function S1 sigma J. So we're going to start from the same state, but apply the different step to it. And it's going to deterministically tell us we're going to go to state S2 prime. And then the only question we have in mind is like, now, is this ending up in the same state S3? So if we take the state S2 prime, and we apply the sigma I from this transition, will we end up in the same state S3? So visually, it looks like almost the same question, but this turns out to be a much easier question to automate because it's purely a bunch of symbolic computation. There's no existential, you have to cook up this S2 prime. It's purely, you compute S3 this way, you compute another version of S3 this way through the bottom path. And you answer the question, are they equal? It's a much more sort of well-formed, decidable, almost, not quite decidable in a mathematical sense, but much crisper question of what we can ask Daphne or Z3. So one thing I wanted you guys to sort of think about is the reading question is almost like, what's in this sigma? And what has to go there in order for this approach to work well? So any questions? The thing I want to do is like actually put you guys into breakout groups, and you guys can chat about whether this, like what you think is ending up in this sigma, and then we'll come back and talk about it as a group. But any questions before this? Make sense? All right. So let me move you into breakout groups, and then we'll come back in 10 minutes or so and see what all this means. All right, sounds good. I didn't stick She and Upamanu into breakout groups because I figured Upamanu will just give away all the answers.
Fair enough.
Yeah. That's kind of like, so one cool thing I was trying to get at actually in this discussion of what's in the sigma is that like this clever memory model is actually quite important to making this commutative diagram work out, because if you try to model, let's say, pointer memory allocation in a naive way, then this step up here gets a new pointer. If you run the other guy, it might get the same pointer now, and now you have to cook up some new S2 prime, like what the hell is going on? How are they equal? But the very clever memory model that you guys have means that it's meaningful to reuse, sort of reorder steps. They're sort of stateless in some kind of a way.
Right.
Got that. You mean the model where the heap is, quote, immutable, unquote.
Yeah, so this,
but you still choose something out of it.
Yeah, so like it's a little bit weird that they say the heap is immutable. It's really like the set of objects in the heap is immutable. That's sort of pre-allocated, and every transition is going to get a very specific object out of the heap. The contents, of course, mutable. But yeah.
Right. It's like the tree and the metadata kind of is meant to be immutable, basically.
Yeah. So this whole forest business. Yeah, I think that. Yeah.
Right.
But
and yeah, I guess the point.
When you do an allocate, it's not deterministic which object you get, is it?
It's deterministic by the sigma, which is weird.
Yeah.
So I would have thought, like, the naive thing is that the result of allocate is determined by the state S. But in Armada, the result of allocate is not determined by S, it's determined by sigma.
Right.
Which is why it's much more likely that sort of crossing these guys left and right is going to work out well, because they don't affect each other's allocations.
Right. So like sigma will basically have the new address that malloc is going to return. And
right.
It requires, and you have to check basically that whatever address you're returning isn't already used on the heap. And if it was, then that's not even a step you're allowed to make, for example.
Yeah. Right.
I'm not getting it.
So I guess
in what way is the address determined by sigma?
Sigma literally contains the address that's going to be returned.
If sigma is like a loop, it's the same sigma the second time around the loop, so but it doesn't get the same object.
Oh, it does. That's the funny thing, yeah.
No, because if you go around the loop and allocate 3 objects, they have to be different.
It's not the same sigma. It's a different sigma for each step. So I guess one higher level
what
point
is
would it be? So I guess
I thought sigma was the program statement.
It's not the program statement. No.
A little bit more than that. Sigma is sort of associated with this particular appearance of the statement in the execution.
Oh, I see. It's okay. Right. It's the pair of states.
Right. So an actual behavior in Armada isn't just the sequence of states, but it's sequence of states as well as a step between every pair of states.
So if sigma is a step between pairs of states, why do we need S in there?
in principle, you don't. You could just say, give me the initial state, give me all the steps, and I can tell you what the states are. Just for convenience, we just hold all the
But
states in
again,
hand
like,
as well.
if sigma had the state in it, then it would be meaningless to try to reorder them. They're just not ordered in that way if it was all in the sigma.
So,
it's
so
actually
sigma
like-
doesn't have the state in it.
Yeah, so it's actually the
But what does it have in it?
So
it
in the
doesn't have
case-
state in it, but it has some information about how the operation executes at that point in the state. And there's some kind of a compatibility property that like this sigma is good enough in this state.
Where does that
Otherwise,
information come from?
so this the state machine transformer that Armada has for every single statement cooks up a sigma that has different contents depending on what the operation is. So for example, if it's a thread create operation, then the sigma for that source statement is going to contain the new thread ID that you got at that point.
So,
And then the transition is enabled if you got a valid thread ID.
so suppose that I put that new thread operation in a loop, and I execute
so
it
every
twice.
time it appears in the trace, it has a new sigma. So sigma is not the source level statement. So the sigma is sort of per appearance in the trace.
So yeah, so there's like a different sigma type for every single statement, basically. So there's, for example, there's like main underscore PC1 sigma is a type, and in your behavior, you'll have one object of that type for each transition of that statement.
Oh. And those objects are not identical.
No, not necessarily.
Exactly in what way do they differ?
Like, so you're saying objects between two different states or for two different statements?
Same statement, but two different occurrences.
You have no idea. They could be, it's just arbitrary. Anything that's allowed is allowed. So like the final theorem that we prove says, if you give me any behavior where you have some sequence of states and steps between them that is valid and coherent, then prove, blah, blah, blah about it. And it could be any, it could be anything that's, as long as it's the transitions are valid, basically.
What makes them valid?
Things like, on a create thread, you can't reuse thread ID. So there's like global state, which keeps track of thread IDs that are used, and it'll require that whatever this non-deterministically chosen new thread ID is, it can't be one that's already used. malloc has like the same thing, like you can't non-deterministically pick an address that's already been malloced or that's already been used, stuff like that.
Oh,
And like, yeah, so like these valid things, for example, allow you to prove that if I do x equals malloc, int, and I do y equals malloc int, I might want to prove that that x and y, the pointers are different, and this validity thing will basically allow you to prove that.
I see. Sort of sounds like prophecy variables. I'm pretty sure it's not,
Yeah.
but it does sound like it.
Yeah.
Interesting.
I think
Yeah, I guess it's like prophecy of like a single step. Like this step, I know exactly. Sigma has the stuff that's going to tell me what's going to happen at the end of this one non-deterministic step. So it's kind of, yeah, I kind of see what you mean, I think.
So here's one way in which it's different from prophecy variables. Prophecy variables typically span a sizable chunk of the execution. It's not sort of right away you're going to use the prophecy variable.
Right.
And here, the prophecy variable is only useful for basically one neighbor. You're only ever going to swap it with your immediate neighbor.
Okay.
Right.
Huh. Well, that's very interesting. I read that bit about the encapsulating non-determinism, but I didn't understand it.
Let's see.
Yeah, I was excited when I figured out what the hell is going on. So that's why I figured I'd talk about it. I'm not sure it's particularly deep, but it is interesting to me. I mean, okay, so I think this is the kind of trick you have to play to help Daphne and Z3 reason about stuff, right? Like, so it's a encoding trick to help instantiate that existential S2 prime in the commuting diagram.
So how do you hook this hack up with there must be something to prove about this hack, that it's okay to do this.
So I think at the bottom level, the execution model of code is written in terms of this weird view of the world that indeed you never reuse pointers, that all pointers are predetermined and all thread IDs are predetermined. And I think that's part of the TCP, that the sort of trust assumption, if you want to state it precisely, is that the real execution of the C code or the Armada code is going to be compatible with this way of modeling it. And they have some kind of an undefined behavior that prevents you from ever comparing pointers, so that you can never discover that pointers got reused.
Right.
Maybe this is not a reasonable question, but you might say, if you want to go from Armada to actual x86 binaries, then you're going to be taking you're going to be hooking Armada up with some model of the actual 86 that you get from the guys in Cambridge, for instance. How is this weird step object thing going to fit into that?
Very different, I think. Yeah, it's like it's probably going to be another level or layer, whatever you want to call it, and it's not going to be a reduction argument. It's going to be something else.
It's going to be something else. Okay.
Yeah.
That we haven't articulated.
Yeah, and I think the paper doesn't actually have a plan. Well, it's weird that they actually use CompSert TSO, because as far as I can tell, that's like a total red herring. Like, they don't connect to those semantics. They don't get any properties. They just use it
just to make you feel better.
And then they find themselves in the evaluation like, oh shit, it's slow. Well, now let's go back to GCC.
So I think we had looked into C++ and tried to figure out whether we could use like C++ acquire release to like to guarantee the TSO semantics we wanted. And none of us were really quite sure if it would work out. So I think Jay emailed somebody and asked about it, and this person wasn't quite sure. He emailed somebody else. It ended up getting to a grad student at a university in Korea who gave a counterexample that you couldn't use it in this way. And we're like, okay, guess we're going to use CompSert TSO. It was silly. Yeah. I mean, the main point of using CompSert TSO is that, like, for example, in this one lock-free queue that we had, to compile it in GCC, we have to add like two memory barriers in places for it to actually work correctly. In CompSert TSO, we don't need to bother doing that.
Right, because they've already sorted that out.
Yeah. What you're getting is like GCC has a weaker memory model than TSO, and moves stuff around for you. I see that.
Yeah.
Have the breakout groups timed out?
Yeah, I think I moved them back. Let's see, did we get everyone back? I think we did. All right, good. So what did you guys decide? What goes in the Sigma? Anyone from, I don't know, the first group want to go? Alex?
Why don't I see anyone else on the screen?
I also don't see anyone on screen.
Oh, I see. Maybe they...
I don't think you got them back.
I see. It's like a 60-second timeout, and they don't want to come back yet. Yeah. All right. Now we got them back. Yeah. All right. Let's try again. Yeah. So what did you guys think about? What's in the Sigma? Did you guys even get to this question? Was it sort of clear or confusing or what? Maybe I'll pick on some people. So
don't hesitate. I was confused.
Oh yeah, we actually had like a lively discussion here with Upamanyu and Butler trying to figure out what the hell's going on. So we're curious to hear what you thought as well. So maybe I'll pick on Alexander. What was your group's discussion?
Yeah, so we talked about, the given case of like an uninitialized variable in your stack frame being kind of like concretized in that Sigma. And just kind of like any other non-deterministic behavior. We were talking for a bit about trying to figure out like what other non-deterministic behavior, other than like the one example they gave, might be. There was like one other section that mentioned like you could have like an if star, where like you have like a branch on like an unknown condition. And
okay, good examples. Yes, actually, I was also thinking about this like branch if star business. So I think the uninitialized memory is like definitely in the Sigma. That's like part of the Sigma state indeed. I think the way the branch actually works out is kind of weird. I think this if star is actually not part of the Sigma, but actually the if star is represented as just like two possible transitions. So it turns out to be like not actually a Sigma. Another way to think of it is that if you have an if star statement, you actually like get sigma, sigma 1 and sigma 2 corresponding to the two branches of the if statement, instead of having a single sigma with the non-deterministic star choice in it. But indeed, I think I spent a while trying to figure out where this if star was in their source code, and I couldn't find it.
I think
on the right.
I think the if star was initially implemented as as being part of the sigma, and we later on decided that all ifs would instead be two different sigma types for true and falses, and so then it became what you just described.
Okay, yeah. So I guess change it. Yeah. Okay, makes sense. So what about the other group? Maybe I'll pick on Julian. What did you guys figure out?
Yeah, so we also a little bit confused, but from our conversations, kind of we felt the idea is that these step objects kind of bundle all the non-deterministic stuff in one kind of section, so the rest of the system can deterministically do everything else. So, like for example, with an uninitialized stack variable, we can basically like give that some sort of value in the step object, so that way we can kind of like abstract away the non-determinism, so that then we can like deterministically do a next step.
Yeah, fair enough. Yeah. Okay, so I should say I sort of cheated. I just looked at their source code, and it took me a while to figure out what the hell is going on in there. It's like a large project. But actually, there's actually two interesting other answers that the paper doesn't actually even talk about. So slightly unfair question, but two important things. One is actually the thread ID. Turns out to be in the sigma. So the sigma actually tells you which thread is going to even take the step. So on previous diagrams, I was like writing this I and J. Actually, it turns out the I and J is inside the sigma. The sigma tells you which thread is going. So that's certainly one non-determinism. Like the biggest source for concurrency is the choice of thread. But the other stuff actually turns out to be quite interesting. It's really, you can think of it as runtime choices. So what I mean by this is that maybe you call malloc to allocate some memory, and this returns you some kind of a pointer. And it turns out this pointer is non-deterministic, right? Like it could be any unused pointer. That's like valid for malloc to return. And the problem is, if this is so non-deterministic or unconstrained, how sure are you that you'll end up in the same exact state S3 when you reorder the two operations? So just to give you an example, so suppose that here, I'll sort of draw this diagram again, maybe with a different color to be concrete. Here, we call malloc, and we get the pointer 5, simplified version of pointers of some sort. And then another thread calls malloc. This is thread 1, thread 2. This guy gets the pointer 7. All right, easy enough. Suppose we swap these threads around. Well, in this case, if you run 2 first, it still does the same malloc. The problem is that in reality, malloc is just going to give away the first allocated object, the first free object. So now thread 2 gets the value 5, and thread 1, when it calls malloc, it's going to get the value 7. A totally legitimate execution, but now you ended up in a different state. Now in this state, what's going on is that thread 1 has pointer 5, and thread 2 has the pointer 7 on their stacks. In this state at the bottom, what's going on is that thread 1 got the pointer 7, and thread 2 got the pointer 5. These are different states, so it's not a mover. This is sort of going to defeat our whole plan of proving movers. And the way that the sigma thing is going to help us is that the choice of the pointer is actually encoded in the sigma, because it is indeed a sort of a non-deterministic choice. And here I sort of chose 5 because that's what's probably going to happen at runtime. You'll get the next available thing, but anything is allowed by the runtime. So this pointer choice, like 5 or 7 or whatever it is actually in the sigma if the sigma is corresponding to a memory allocation operation. Same thing if you have a thread create, then there's a new thread ID here. And the new thread ID is the same kind of a non-deterministic object that you get back. And the choice of the new thread ID is in the sigma. And the way to think of it is that by putting the stuff into the sigma, we are carefully encoding in Armada all the information about how that step ran in the trace. So for example, here, the sigma j describes exactly what choices this step took here, so that we can carry over those same choices when we permute the operations. And in this way, we can basically help the Daphne and Z3 system instantiate this S2 prime. And if we get this encoding right, then we can sort of meaningfully take the non-determinism of one operation and carry it earlier, take the other guy, move it later, and it's still a meaningful transition. Kind of a tricky low-level detail in some sense, but I think it's actually kind of crucial for them in order to use Daphne effectively.
So is this right? What this does is to change the existential quantifier on the intermediate state into a universal quantifier.
Absolutely, yeah. So I think it figures out where to get that existential quantifier in the original trace. In some sense, it's like a plan for how to instantiate that exists S2 prime, and the instantiation is exactly this sigma j. And they carefully syntactically construct these sigmas so that this instantiation will make the proof work out most of the time.
Yeah, Butler, I don't think it's what you said. I think it's all existential quantifiers.
It says that no matter what values you choose for these non-deterministic choices to wire into the sigmas, it still works.
I think this proof can fail if this is the wrong existential to give in the second execution.
I should say,
so it's sound, but it's incomplete.
Their real encoding, right? Like their encoding has no existential. This question of equality of these two formulas is literally what Armada poses to Daphne. And as a result, the existential quantifier is only in some meta theory in the author's heads.
Yeah.
Or in our
Right.
heads.
Right. Exactly.
Yeah.
Yeah. If you want to compare this to reduction, right? So like in reduction, you would normally be allowed to give an existential there. They're not going to give an existential. Or they are, like their witness they're always going to give is the same that they got in the first execution. And then their sigmas are carefully constructed. As Nikolai said, the sigmas are carefully constructed so that this basically always works.
Yeah. All right, so hopefully that made some sense. This seemed like a kind of a cute detail. I was excited about it when I looked at the source code for a while and figured it out. Hopefully it's give you some sense of like what it takes to formulate your problem in a way that's friendly to automation. So here's maybe a little small window into like what's the difference between doing proofs in Coq and in Daphne. I think in Coq you don't really worry about this kind of instantiation nearly as much. You just say the natural thing we drew on the diagram on the previous slide. You say there exists, and you go to town trying to prove it, and it's fully general, all great, and you have to manually generate the proof. But these kinds of things are hard to prove mechanically. They require a lot of proof effort. And these kinds of tricks we're looking at this slide, where you carefully formulate the problem so that you avoid the need to instantiate stuff or carefully specify non-obvious things at proof time, that's what makes this approach work well with automation, because the whole problem is carefully formulated so that it's easy to answer some of these questions that otherwise would have required you to type an exists statement in Coq and similar things like this. It's hard to fully appreciate from this 5-minute description, I think. There's a lot of details like this that are low level, but actually turn out to matter quite a bit. The flip side, the one actually interesting discussion we had while you guys were in the breakout room is what would it take to actually prove that this is correct all the way down to assembly? And the problem is actually assembly doesn't follow this model of execution, right? So in Armada's model of execution, every time you call malloc, you get a new pointer that no one else has ever seen before. And this is important that no one else saw your pointer before, so that you can swap with someone else. God forbid, you're going to get into a situation where you had pointer 5 that was just allocated, and the guy before you just freed pointer 5. For some stupid reason, you're now not going to be movers, because you can't use pointer 5 before he freed it. So Armada avoids this by having this model where you never use pointers or memory addresses. But this is not real, and you would need quite a new kind of a proof to prove that Armada's model of the world is a sound version of the way real assembly code, for example, might run. That's an interesting question, how to push it through and what limitations this might pose, but it's kind of an interesting tidbit about what it takes to carefully orchestrate your model to be automatable. Makes sense to some extent? Any questions about this? All right, so that's all the time we had to talk about Armada. Hopefully this gives you some sense of what it takes to do a formal proof of correctness about concurrent code. For all the machinery that we talked about, this is probably not even half of Armada. There's many more details the paper talks about. And even that, like they're able to achieve, proofs of pieces of code that are maybe like 30, 40, 50 lines long. So you can sort of appreciate this is a tricky problem. They're proving a 50-line concurrent data structure with, maybe hundreds of lines of proof, but it's not thousands or tens of thousands, which is maybe what some prior systems would have done. This is a really hard problem and sort of still an open problem. What's the right way to do it? What's the right way to think about it, etc. But this is sort of where the state of the art kind of is now. And then on Tuesday, we're going to take a look at Iris, which is also state of the art, but coming at it from a language direction instead of a state machine direction to reason about concurrency. And hopefully that'll give you some interesting contrasts to think about there.
To expand just a tiny bit on what Nikolai just said, if you read the evaluation section, you'll see that Armada is in fact generating tens of thousands of lines of proof for Daphne to dispatch. But,
Indeed, yeah.
but that's perfectly okay. That's just like, we don't care about the fact that when you run Coq, it's executing billions of instructions.
That's right.
And similarly, we don't really care about the fact that Armada is generating 25,000 lines of source lines of proof for one of these guys because we never see them.
That's right. But maybe one way to make this real for you guys that have used Coq, probably all those 20,000 lines of stuff are what you would have probably had to type into Coq in order to make this proof go through there. So Armada is perhaps pretty helpful if you were to take this approach in Coq. You probably would have taken the Iris approach, we'll talk about next week, and that ends up being less code for other reasons, but maybe that gives you some sense of where this is floating in sort of this giant space of all the possibilities of how to do the proof. All right, so that's it for Armada. See you guys next week. We'll talk about Iris.